then iron, and has greater oxidation potential than iron, but still it do not corrode easily. This is because of the formation of a tough layer of chromium oxide over a tough layer of chromium oxide over the surface of chromium, which acts as a protecting coat and prevent chromium from further corrosion. That is why chromium do not corrode easily.
Welcome to Solver Fee.
Okay, Chapter 2, Problem 109. We have a rectangular plate suspended by 3 cables, and we need to determine what the weight of that plate is, given that the tension in cable AC is 60 newtons. So in this free body diagram that I have drawn to the right here are all of the forces acting on point A. We have the upward reaction force, which is just equal and opposite of the weight of the plate. So I'm just going to label that as W because that is the value that we're searching for. And then I have the tensions in each of the 3 cables. I do not have all of the dimensions drawn in here, but you can get those directly from the diagram in the textbook. What I do have here to the left are these 3 equations. These are actually the directional vectors of each of the 3 cables running from A to B, A to C, and A to D. And you can get the values here just by looking at the dimensions listed in the textbook and using the coordinate system that's given, which I also have copied here. So what we need to find for this problem is the value of W. And we're given that the tension in cable AC is 60 newtons. What I'm going to do first is label these cables just to make them a little bit easier to work with. Cable AB will be cable 1, A to C will be 2, and A to D will be 3. So we are given that the tension in cable 2 is 60 newtons. And what we need to try to find is W. W is acting entirely in the y direction. So let's consider all forces acting in the y direction. This is a statics problem, so of course all forces acting in every direction, including y. is 0. And let's take a look at which forces are acting in the y direction. Obviously, we have our upward W force, and then we're also going to have the vertical or Y component of each of the three cable tensions. So this gives us an equation: weight plus T1y plus T2y plus T3y. Set that equal to 0. So let's take a look at this component here, T2y. We are given the value of T2. From that, we should be able to calculate T2y just by multiplying our tension by a ratio of the y dimension of the cable. Call that d2y over the length of the cable, which we'll call d2. We can calculate the length of that cable just by the Pythagorean theorem. We use each of the three dimensions of the cable. So for the x dimension, we have 450 millimeters, the y dimension 480, and the z dimension of 360. So we take the square root of 450 squared plus 480 squared plus 360 squared. That gives us a total length of 750 millimeters. Now we go back to d2y. We just take our T2 value of 60 newtons, multiply it by a ratio of d2y, which is that 480. It's negative 480 over our d2 of 750 millimeters. That gives us a T2y value of negative 38.4 newtons. Let's plug this back into our equation for sum of the forces in the y direction. We get W plus T1y, and I'm going to move the T2y to the other side of the equation to get rid of the negative. And that's what we have now. So we need to find our T1y and our T3y in order to find our W. Now let's consider the sum of the forces in another direction. Let's go with Z. Of course, sum of the forces in the Z direction are also equal to 0. Which forces are acting in the Z direction? We will not have W this time because that is only acting in the Y direction, but we will have the Z component of the tension in each of the three cables. So that gives us T1Z plus T2Z plus T3Z equals 0. What I'd like to do, since we're looking for W and it's really this equation that matters the most, I would like to put this new equation for the sum of the forces in the Z direction in terms of their y components rather than their z components. So we'll take the first one, T1z. We have a formula for T1z just by we can relate T1z to T1y with a ratio of their dimensions. So in order to get T1z from T1y, we multiply T1y by a ratio of the cable's z dimension over the cable's y dimension. That gives us T1y times our z dimension, which is 360 millimeters, over its y dimension, negative 480 millimeters. It gives us negative 0.75 T1y. Now we just do the same, we use the same formula for the other two cables. So we do T2z equals T2y times our dimensional ratio, T2z over T2y. Now we actually know T2y because we solved for it right here. It's this negative 38.4 newtons. Multiply it by its ratio, our z component is 360 millimeters over our y component of negative 480 millimeters. That gives us a z component in cable 2 of 28.8 newtons. Lastly, we do the same for cable 3. Take T3y, multiply it by our dimensional ratio. That dimensional ratio is negative 360 millimeters for our z component, negative 480 for our y component. That gives us 0.75 T3y. So now that we have all of these values, let's plug that into our equation for the sum of the forces in the z direction. We get negative 0.75 T1y plus 28.8 plus 0.75 T3y equals 0. Now what I'm going to do is solve this equation for just one of these variables, because there are two unknown variables in here. If I solve for one of these variables in terms of the other one, that's going to come in handy later on. So we have T3y, which I will solve for. That gives us T1y minus 38.4. Okay, so now we have one equation with two unknowns. What I'd like to do is find one more equation relating our T3y and T1y, because then I will have two equations, two unknowns. I'll be able to solve for both of them, and then we'll be able to plug those values into this equation and solve for W. So now let's consider the forces in the last direction. We haven't yet checked x direction. Sum of the forces, again, is 0, of course. And which forces are acting in the x direction? We will have the x component of each of the three cables. And again, we will not have our w component because that we will not have our w force because that is only acting in the y direction. So our formula, our equation becomes t1x plus t2x plus, oops, that should be a t, 2x plus t3x equals 0. Now, I'm going to do something very similar to what I did earlier with this equation, where I want to put this one in terms of its y components rather than its x components. So, and we can do that very similar way to how we did it last time. We just take, in order to get the x component of the tension from our y component, we multiply it by a ratio of its x dimension of the cable over the y dimension of the cable. So this is T1y times our x dimension. Cable 1 is negative 320 millimeters. Our y dimension is negative 480 millimeters. This simplifies to 2/3 T1y. Now we do the same for the other two cables. Cable 2, take the y component, multiply it by the x dimension over the y dimension. And again, we know T2y directly, calculated it earlier, that is negative 38.4 newtons times our x dimension is 450 millimeters over our y dimension, which is negative 480 millimeters. This gives us 36 newtons. Lastly, cable 3, we get T3y times x dimension over the y dimension for cable 3, which would be 250 millimeters over negative 480 millimeters. I am just going to leave this as a somewhat complicated fraction here. T3y. Okay, so now we have our x components in terms of their y components. I'm going to substitute these values back up into this equation. We get 2/3 T1y plus 36 newtons for T2, and then minus 25 over 48 times T3y equals 0. So now we have our second equation relating T1y and T3y. I'm going to plug in this value for T3y from this equation here. So that becomes 2/3 T1y plus 36 minus 25 over 48 times, and here's our substitution. T3y, we have T1y minus 38.4. Set that equal to 0. And we just solve this equation for T1y. That leaves us with T1y equals negative 384 newtons. I take our formula for T3y from before, T1y minus 38.4 newtons, using that value for T1y, and we get a T3y value of 422.4 newtons. So now let's look back at our equation for the sum of the forces in the y direction one more time. We have W plus T1y plus T3y equals 38.4. Substitute these values of T1y and T3y into that equation. That equation becomes W minus 384 newtons minus 422.4 newtons equals 38.4 newtons. You can easily solve this equation for W, and we get our W, which is the weight of the plate, at 844.8 newtons. And that is our final answer.
To calculate the equilibrium constant, K for the given equation, in which the Hg2 plus 2 form Hg0 plus Hg2 plus. In this reaction, Hg plus oxidizes into Hg2 plus, releasing an electron. The E oxidation of the Hg plus is minus 0.92 volt. On the other hand, the Hg plus gain electron from Hg0 oxidation state, so the E reduction is equal to plus 0.80 volt. Adding the two half cell potentials, we will get E naught of the cell, which is equal to E oxidation plus E reduction, so the sum of the two values is equal to 0.12 volt. Now to calculate K, we know that E naught is equal to 0.0592 divided by N into log of K, where log of K is equal to E naught into N divided by 0.0592, or K is equal to NT log of E naught, so the value of E naught is equal to 0.12 volt multiplied by N. N is the number of electron lost and gain in the reaction, which is equal to 1 divided by 0.0592. So K is equal to, calculating the value and then taking NT log, we will get that K is equal to 9.39 and to 10 raised power minus 3, which is the required answer to the question. To calculate the equilibrium constant, K for the reaction in which 2H2O2 form 2H2O plus O2. So E naught of the cell is E naught for this reaction is equal to 1.78 volt. To calculate the K, we have the equation that E naught is equal to 0.0592 over n log of K. So log of K is equal to E naught multiplied by n divided by 0.0592, or K is equal to nt log of E naught. E naught is equal to 1.78 volt multiplied by n. N is the number of electron lost or gain in the reaction, which is equal to 2 divided by 0.0592. K is equal to nt log. Calculating this value, we get 60.13. Taking the nt log of 60.13, we get the value of K, which is 1.36 into 10 raised power 16. This is the required answer to the question. The sketch of the lead storage battery is lead storage battery is very simple one, in which there are in a cell of the lead storage there are two half cell, in which there is lead electrode dipped in 1 molar H2SO4 solution. On the other hand, there is a lead oxide electrode. So the lead oxide electrode is also dipped in H2SO4 solution. At anode, the lead react with H2SO4. It oxidizes, forming PbSO4, and 2 hydrogen ions are released from the sulfuric acid with the release of 2 electrons. E oxidation of this cell is 0.296 volt. On the other hand, at cathode, the lead oxide gain the hydrogen ions and the electrons released by that, and the presence of HSO4 minus, it form PbSO4 plus water molecule. Here the E reduction is equal to 1.628 volt. Combining the two half cells, so E naught of the cell is equal to E oxidation plus E reduction. The sum of the two values is equal to 1.924 volt, which is approximately equal to 2 volt. Now to calculate the K equilibrium constant for this cell, so as we know the equation that E naught is equal to 0.0592 divided by n log of K, or K is equal to nt log of E naught n to n divided by 0.0592. Putting the values, K is equal to nt log of E naught is equal to 2, where n is equal to the number of electron lost and gain, that is also equal to 2 moles of electron, divided by 0.0592. Calculating the value and then taking the nt log, we get the answer, that is 1 into 10 raised power 65. In order to calculate the non-standard cell potential E cell, which is equal to E naught of the cell minus 0.0592 divided by n into log of K, putting the values, E cell is equal to E naught of the cell is equal to 2 volt minus 0.0592 divided by n is the number of electron lost and gain, that is equal to 2 electrons, and log of K is equal to 10 raised power 65. E cell is equal to 2 volt minus 0.0296 when we divide 0.0592 by 2, so we get 0.0296, and log of 10 raised power 65 is equal to 65. So E cell is equal to 2 minus the product of the two values is also approximately equal to 1.924, which is equal to 2. So E cell is equal to 0 volt. This is the voltage of the cell when the reaction is in equilibrium value. These are the required solution to each part of the question. For a cell in which HgO react with water molecule in the and gain 2 electrons to form mercury and hydroxyl ions. On the other hand, the E naught of the cell of this reaction is 0.098 volt. On the other hand, the zinc oxide in the presence of water molecule to gain 2 electrons form zinc and 2 hydroxyl ion, so E naught of the cell is equal to minus 1.260 volt. So in this reaction, zinc is oxidized while the mercury is reduced. So when zinc react with the 2 hydroxyl ions forming zinc oxide and water molecule, here 2 electrons are released So the E oxidation of the zinc is equal to 1.260 volt. On the other hand, the mercury oxide react with the water molecule and gain the electron lost by the zinc, form mercury and 2 hydroxyl ion. E reduction is equal to 0.098 volt. Adding the value of E oxidation and E reduction to get E naught of the cell, we get it is equal to 1.358 volt. Adding the two equations, we can cross the hydroxyl ions and the electrons as well as the water molecule. So the simple equation or overall equation is that zinc react with mercury oxide, forming zinc oxide, and mercury is formed. Now to calculate delta G naught for this cell, we know delta G naught is equal to minus NF E naught. So delta G naught is equal to minus, where N is the number of electron lost and gain, which is equal to 2 moles of electron. If a Faraday constant 96,500 coulomb per mole of electrons, multiply by E naught of the cell, 1.358 volt. Delta G naught for the reaction is minus 2 multiply by 96,500 coulomb multiply by 1.358. Instead of volt, we can write joule per coulomb because 1 volt is equal to 1 joule per coulomb. So calculating the value, delta G naught is equal to minus 262,094 joule. To change it into kilojoule, we will divide it by 1000. So delta G naught is equal to the minus 262.094 kilojoule. Now to calculate the K for the reaction, so we know that E naught of the cell is equal to minus 0.0592 divided by N into log of K, or K is equal to NT log of E naught into N divided by 0.0592. So K is equal to NT log of E naught value is equal to 1.358 multiplied by N is equal to 2 divided by 0.0592. So K is equal to 7.56 into 10 raised power 45 when we calculate the NT log of the above equation. Now to calculate the E of the cell, when sodium hydroxide is added to both the compartment, so E cell is equal to E naught minus 0.0592 divided by N into log of QRK. So E cell is equal to E naught 1.358 volt minus 0.0592, where N is equal to 2, and log of K is equal to log of 7.56 into 10 raised power 45. So E cell is equal to 1.358 minus 0.025 0.0296. When we divide 0.0592 by 2, we get 0.0296, and log of 7.5 into 10 raised power 45 is equal to 45.878. When we multiply these two values, so E cell is equal to 1.358 minus 1.358. So there is no change in the cell. So E cell is equal to 0. It means there is no change in the cell potential because hydroxyl ions are equal on both sides. We can also calculate the E cell by calculating the E reduction and E oxidation separate in two parts. Also calculate the E reduction. So E reduction is equal to E naught reduction minus 0.0592 divided by N, where N is equal to 2, and log of hydroxyl ion concentration on the reactant hand side, it is square. If we increase the concentration of the hydroxyl ions by tenfold, so E reduction is 1.3, E reduction is 0.098, 0.098 volt minus 0.0592 divided by 2 is equal to 0.0296, and log of when the concentration of the hydroxyl ion is increased by tenfold in the reduction half. So E reduction is equal to 0.098 volt minus 0.0296, where log of 10 raised power 2 is equal to 2. So E reduction is equal to 0.0383 volt. On the other hand, E oxidation will be equal to E naught oxidation minus 0.0592 divided by 2 log of 1 over the hydroxyl ion concentration square. So if we increase the hydroxyl ion concentration by tenfold, so E oxidation is equal to E naught oxidation is equal to 1.26 volt minus 0.0592 divided by 2 is equal to 0.0296, where log of 1 over 10 square. So E oxidation is equal to 1.26 minus 0.0296, and log of 1 over 100 is equal to minus 2. So E oxidation is equal to 1.26 plus 0.0596, which is equal to 1.3192. Now to calculate the E cell, we will add the E oxidation plus E reduction. So this is equal to 0.098 volt plus 1.3192 volt. The sum of the two values is equal to 1.35. 1.358 volt. So it means there is no change in the potential of the cell when we add hydroxyl ion by tenfold to each half. These are the required answer to this part of the question, where this is the E naught of the cell, this is the value of delta G naught, and this is the value for the equilibrium constant of the cell. To calculate the E cell for the fuel cell in which 2H2 plus O2 form 2H2O, here hydrogen oxidizes forming 4 hydrogen ions and 4 electron, as E oxidation of the hydrogen is 0 volt. On the other hand, oxygen in the presence of 4 hydrogen ion gain the 4 electrons, form 2H2O, so the E reduction for this cell is 1.23 volt. Now the E of the cell, E naught of the cell, is equal to 1.23 volt, which is the sum of E oxidation and E reduction. To calculate the delta G naught for this cell, the equation is that minus NF E naught, putting the values, delta G naught is equal to minus, where N is equal to 4 moles of electrons. F is Faraday constant 96,500 coulomb per mole of electron, and E naught is equal to 1.23. Instead of volt we can write joule per coulomb, because 1 volt is equal to 1 joule per coulomb. So calculating the value, delta G naught is equal to minus 474,780 joule. To change it into kilojoule, we will divide it by 1000, so minus 474.78 kilojoule is the value for the delta G naught. Now to calculate the equilibrium constant K for the reaction, we say that log of K is equal to E naught N to N divided by 0.0592. This is the modified equation. So K is equal to NT log of, where E naught is equal to 1.23 volt, N is equal to 4 divided by 0.0592. So K is equal to NT log of, the answer of the calculation is equal to 41.55. So K is equal to NT log of 41.55 is equal to 3.5 into 10 raised power 41. Now we have to calculate the E cell, which is equal to E naught of the cell minus 0.0592 divided by N, and log of Q, where log of Q is equal to E cell is equal to E naught of the cell is 1.23 volt minus 0.0592 divided by N is equal to 4 mole of electrons, and log of, there is 1 over the oxygen ion concentration, into hydrogen oxygen gas concentration and the hydrogen gas concentration square. Because these two are at the reactant side, at the product side there is only water molecule, so we do not write the concentration of pure liquid. As the pressure is equal to 1 atm, so PV is equal to nRT, or P is equal to CRT, or C is equal to P divided by RT. So calculating the concentration for hydrogen or oxygen, P is 1 atmosphere, where R is 0.0821 liter dm cube per mole per Kelvin, and temperature is 298. So the concentration of both the gases is equal to 1.022. Putting the values for the hydrogen and oxygen in the above equation, we get that E cell non-standard cell potential is equal to 1.23 volt minus 0.0148 and log